Stage builders solve a different class of protocol problems. Object construction, where certain fields are required and must be provided in a specific order. The core insight is that we can use the type system to track not just what the state an object is in, but what information has been provided during its construction. In our HTTP client builder example, we are not tracking the state of a single object over time. We are tracking the completeness of information needed to construct a valid object. Each interface represents not a behavioral state, but a knowledge state. Host step means I know we need a host, but don't have one yet. Port step means I have a host, but still need a port. And ready step means I have all the required information and can build the final object. The key insight is that each step interface has methods that returns the next step interface. This creates a linear progression through the construction process that cannot be bypassed or reordered. You literally cannot call build until you've progressed through all the required steps because the build method exists only on the ready step interface. The builder implementation class implements all the step interfaces simultaneously, just like our database example. But instead of representing behavioral states, it accumulates the information needed for construction. When you call with host, the implementation stores the host value and returns itself, but cast to a port step interface. The object hasn't changed behaviorally. It just gained some information and changed its type level identity. This pattern enforces exactly one semantics for required fields. You cannot skip the host step because there is no method on host step that leads directly to ready step. You cannot provide the host step twice because once you have a port step reference, there's no with host method available. The type system makes it impossible to construct an incomplete or incorrectly configured object. The power of stage builders extends beyond simple field setting. You can enforce dependencies between configuration options. Perhaps SSL settings are only available after you've specified HTTPS. Or certain authentication methods are only valid with specific protocols. Each stage can expose different methods based on what makes sense given the information provided so far. The pattern also provides excellent developer experience through ID autocomplete. At each stage, developers see only the methods that are valid for the current configuration state. Instead of seeing an overwhelming list of all possible configuration methods, they see just the next valid step in the construction process. Stage workers work particularly well for configuration objects, fluent APIs, and domain specific languages embedded in general purpose programming languages. They're commonly used in HTTP client libraries, SQL query builders, and testing frameworks where complex objects need to be constructed with many independent options. Refinement types address a fundamental limitation of the previous three techniques. The previous three techniques only track which methods have been called, not the values that were passed to those methods. Sometimes protocol correctness depends on the actual data values, not just the sequence of operations. Consider a buffer with read and write operations. The traditional approach would track whether the buffer is readable or writable as states. But the real constraint is more nuanced. You can only read from positions that have been written to. This depends on the specific offset values being used, not just whether read or write operations have occurred. Refinement types extend the type system with logical predicates. Instead of just saying this parameter is an integer, we can say this parameter is an integer greater than 0 and less than the current write position. The type system has enough information to verify at compile time that the protocol constraints are satisfied. In our buffer example, the valid offset type isn't just an integer. is an integer that satisfies the predicate that n has to be less than equal to the right offset. When you call read with an offset parameter, the compiler must prove that your offset value satisfies this predicate. If you try to pass an arbitrary integer, the type checker will reject your program. The verification happens through a combination of type checking and logical reasoning. When you write offset is equal to 5 and the current write offset is known to be 10, the compiler can prove that 5 is less than equal to 10 and allow the operation. However, if the write offset is 3, then the compiler can prove that 5 is less than equal to 3 is false and reject the operation at compile time. For a bank account example, the transfer method has a precondition that the amount must be positive and the balance must be sufficient. The type system verifies these conditions before allowing the method to execute. If you try to transfer a negative amount or more money than the account contains, you get a compile time error, not a runtime exception. Now, the power of refinement types is that they can express arbitrarily complex constraints involving arithmetic, logic, and relationships between multiple values. You can specify that an array index is within bounds, that a network timeout is within reasonable limits, or that a cryptographic key has the correct length and format. The compiler uses automated theorem provers, SMT solvers, to verify that your code respects these constraints. However, this power comes with complexity. The type annotations become more verbose as you specify the logical predicates. The verification process can be slow for complex constraints, and sometimes the automated theorem prover cannot verify conditions that are actually true, requiring manual proof hints. Additionally, refinement types are available in specialized languages or as extensions to existing languages, not as mainstream features. Refinement types represent the cutting edge of type safe protocol design. They can express constraints that are impossible to encode with state based approaches, providing mathematical guarantees about program correctness. But they require significant tooling investment and developer expertise to use effectively.